And sir, will you upload the slides on Moodle?
Moodle, it is not possible. That is what I have been told by Professor Krishna Hanumantu last year itself, because the thing will be too large thing if everyone has to do that. So I don't think the CMI Moodle has that kind of capacity. That is why last year itself he had suggested to post it on
not video. I'm talking about the slides.
That's what I'm saying. The slides you can see in the YouTube, and soon you will be getting the notes. Okay. All right. So this is where we had stopped last time. The slides, it is not possible to put it on the Moodle. That's what I was told.
But say in any way, in any circumstance, your notes will be put up in Moodle, right? The notes.
Like last time, I think you were all, most of you have been with me last year itself, first semester or second semester. So that's what we will continue to do.
Okay. So both the notes and the video will be available in Moodle, right?
Notes will be available in Moodle. Video will be available in YouTube.
Okay.
And the link to YouTube is being sent to you.
Okay.
The practice I had done last year on the advice of Professor Krishna Hanumantu, I plan to continue.
Okay. So
yes.
So basically the YouTube link to the video will be there in the Moodle, right? The link.
Yeah. It will be in your. It will be coming to your email anyway. Like last class also. That's what we did. No.
Okay. Yeah. It will come to email. Okay. And the notes will be there in Moodle. Okay, sir.
All right. So this is where we had stopped. So today we will look at conditional probability. Again, something which you are quite familiar with. So this, as you know, this is also related to independence. Now let A and B two events such that probability of A is strictly positive. And the conditional probability of B given A, which is denoted probability B given A, is defined by that conditional probability. Probability B given A is probability of A intersection B divided by probability of A. If probability of A happens to be 0, then this quantity is undefined. And you can easily see if this A and B happen to be independent events, and if P of A is greater than 0, then this conditional probability is precisely PB. That is very clear from this equation. So that also concurs with our intuition that the occurrence of A has no effect on the probability of occurrence of B. So this conditional probability is sort of, if you observe that the event A has happened, on the basis of that, what could be a kind of estimate or probability of. That's it. Okay. Okay. Yeah, elementary result. Yeah, yesterday it was. Yeah. Suppose A1, A2, AN are events. They are all members of script A. And if you take this n-1 up to AN-1, that take their intersection, and that is strictly positive, then the probability of the intersection of all these n guys is given by probability of A1 multiplied with probability of conditional probability of A2 given A1, then A3 given A1 intersection A2, and so on. And finally, I think somebody's audio is not muted, please. Kindly switch it off. And finally, probability of AN given the intersection of the n-1 guys. So again, you would have seen this. This is a very simple exercise. So since this is given to be strictly positive, this, for example, is going to be greater than 0, and all these things are greater than 0. Consequently, all the quantities which occur on the right-hand side, that is, all these conditional probabilities, are all well defined. So that is the first. Okay. So by definition of conditional probability, this proof is very simple. Consider the right-hand side of that, what we have denoted by spade suit, and that can
Sir,
be.
can you just go to the previous slide? Previous slide.
See, this is all you are familiar with.
Okay, sir. Okay, sir. Okay, sir.
The right-hand side is precisely this. You can easily see, because I have just expanded out all these conditional probabilities. And then these, for example, P of A1 will get cancelled with here, that this one. This will cancel with this, and so on. And what will survive finally is basically that's the left-hand side of this. That is this term, the numerator here. So it is a very simple proof. Most of you would have seen it. Yeah, here. Okay. Yeah, simple example. Suppose it is again in a kind of example you would have seen in your earlier courses. Suppose it is known that 10% of a population has a particular disease. So a routine test for this disease is done. And suppose 5%, that is 5% of the healthy people are declared positive by the test. So that is, among those who take the test, the 5% is declared positive by the test. That is false positive. I mean, the healthy people, a person who is healthy, who takes the test, there is a 5% chance that he might be incorrectly diagnosed as being positive. I mean, having the disease. And on the other hand, 85% of the actually affected people are declared positive by the test. So if a person is declared positive by the test, what is the probability that he has the disease? So that is. So in times of this COVID, etc., this kind of situation seems to be, I mean, very much in the news. Okay. Let us denote by capital B1 the individual having a disease, the disease. And B2 is the event, its complement. The individual does not have the disease. And A is the event that the tested individual is declared positive. So this is kind of notation to sort of see what. Again, you would have seen such problems earlier. It is not working. So we are given probability of B1 is 0.1. That is 10% are affected. Therefore, probability of B2 is 0.9. And all this B2 denotes the healthy population. So among the healthy population, if they take the test, 5% are detected to be positive, or actually declared to be positive. So probability of A given B2 is 0.05. And the probability of A given B1, actually an affected person, if he is tested, the probability of his being declared positive is 85%. So we need to find probability of B1 given A. Okay. Okay. So this is what we have to find. So by definition of conditional probability, P B1 given A is this. And the denominator, probability of A, can be written as probability of A intersection B1 plus probability of A intersection B2. Remember that B1 union B2 is the whole space. So you can write this as in terms of the conditional probability and probability of B1. And similarly, this can be written this way and this in this fashion. Now note that in this expression, all the quantities are known. Therefore, we have that plugging in those values, we get this. And of course, it turns out to be approximately so this example is a special case of a result. So a crucial observation here is that this B1 union B2 is the whole space. So B1 and B2, they are mutually exclusive because one is the complement of the other, and they sort of span the whole space omega. And of course, for all these things to make sense, the certain probabilities allowed to be positive. And that result goes by the name of Bayes rule. So let A1, A2 be a finite or a countably infinite sequence of mutually exclusive and exhaustive events. Mutually exclusive and exhaustive means, of course, all these AIs are in script A, that's schema algebra, and any two of them is joined. So AI intersection AJ is the empty set if I is not equal to J. And all the AIs put together, they form the omega. Nothing is left out of the AIs. So assume that P of A1 is strictly positive. And let now C be an event such that probability of C is strictly positive. So in some sense, of course, and this theorem says that in such a case, for any fixed K, the conditional probability of AK given C, that is, if C has been known to have occurred, if C occurs. So with that knowledge, if you want to sort of find the conditional probability, then that is given by this expression. Probability of C given AK times probability of AK divided by this totality of all these things, summation of this. Something like this we had seen in the earlier example. See this expression. So this is because B1 and B2 together, they span the whole space and they are also mutually exclusive. So the proof is very simple. Of course, this is a quite a well known.
Sir,
Yes.
I have a question. So basically here we have a convergence issue in the denominator.
Pardon?
We should have a because if the sequence A1, A2 is not finite, say countably infinite, then the
There will not be any
must
convergence
converge.
issue because see, all these AIs are all strictly less than 1. Okay. And they are all disjoint. So probability, the summation is going to be 1 because probability of omega is 1.
No. I am not saying it. I am saying it in the expression of probability of AK given C. The denominator has a convergence issue because it is an
And that's why
infinite
I'm
sum.
saying there is going to be no convergence issue because this conditional probability again is dominated by 1. So this denominator and absolute value will be dominated by summation P of AI. And summation P of AI is equal to 1 because of this condition, right?
Okay.
Uh,
Okay, fine. Yeah, yes, because summation P of AI is 1, signal wave 1. Yeah.
Please, my request is instead of wasting time, before you ask a question, please think for some time. Then you might see yourself the answer, which will also increase your confidence. Asking questions is fine, but very often if one asks and that turns out to be fairly trivially, it can be fixed. It can also affect one's confidence. For your own good, I'm saying. After all, the motivation or the principle about this thing of the goal of many of these courses is not to load you with everything known under the sun in the subject or anything like that, but to some extent, as far as possible, to instill some kind of a confidence in you that you yourself can learn. If always you have to depend on somebody else to learn, then that is not going to be very productive in the long run, especially in today's world. You will have to learn many things on your own. Okay. Sorry for that, but anyway.
That's really going to discourage questions from us if we have to think about.
Not like that.
If I have to worry about a lot about, oh, is this a stupid question? Then I will prefer not to ask questions. That is what's going to happen.
I am very sorry if I have conveyed this impression. I am extremely sorry. Even if you think it is a stupid question, but if something is again and again repeatedly asked, it could affect your confidence. Okay? You can ask, there is no question is really stupid. Okay? And I also make stupid statements and even ask stupid questions. I am very sorry if I have conveyed that impression. That is not the intention. Okay?
Thank you for clarifying.
Yeah. The intention is that you should have some kind of a confidence. And also, especially some of these things you might have seen earlier. Okay? So please, if I have conveyed that impression, I am extremely sorry. Maybe I should not make such comments hereafter. All right. Okay, let us look at the proof. So verify that both sides of the above equation are meaningful. Now note that C can be written as union of AI intersection C. And this union is a disjoint union. Hence, P of C is equal to summation of this because this is a disjoint union. Also, probability of AI intersection C is PC given AI times PI, P of AI for every I. Therefore, the required conditional probability of AK given C, which is this ratio, and this denominator can be written in this fashion because of here, and each of these can be written in this way, and that is what is required. So mathematically, this is a very simple result. Okay, again, I'm very sorry for having conveyed a wrong impression. Please ask questions, even if it is turns out to be not a very deep question. Any question is welcome. I like questions. Okay. So we will now look at one of the classical examples which involve this conditional probability. Again, something which you would have seen earlier. So an urn has R red balls and B black balls. So a ball is drawn at random from the urn and its color noted. Then the ball which is drawn together with C balls of the same color are added to the urn. This procedure is repeated so that the number of drawing made from the urn is n. Okay. So now let us denote by R sub j the event that the jth ball drawn is red. And Bj is its complement, that the jth ball drawn is black. Then it is clear that probability of R1 is R divided by R plus B, and probability of B1 is B divided by R plus B. So now verify the conditional probabilities. This is again from the what we are given. This is simple. So at each stage, C balls of the same color as the drawn ball are added. So if P of R2 given R1, so if the first ball drawn happens to be red, then at the beginning of the second stage, there will be R plus C red balls. And of course, the total number of balls is R plus B plus C.
Sir, can we just go to the previous slide?
Yeah.
So when you are saying that the total number of drawing made from the urn is n, that means we have performed the experiment n times, right?
Yeah.
Okay, okay. And so can you just once again I just want to know the last statement in the previous slide. Okay, sir. Okay, sir. Okay, sir. Okay, sir.
So these conditional probabilities are easy to check. And similarly, if the first ball drawn is black, then the number of red balls in the urn at the beginning of the second draw doesn't change. It is same as the initial thing. So it will be R. So it will be this. Whereas now the black balls will be more. Therefore, that probability is given. Okay. So now using this information, one can calculate probability of R2. That is probability that the second draw resulted in a red ball. Since the first ball has to be either red or black, this is going to be P of R2 intersection R1 plus P of R2 intersection B1. And using the equation for conditional probability, P of R2 intersection R1 can be written as P of R2 given R1 and then multiplied with P of R1. And similarly here. So in this equation, all the quantities here we know. We have found out these things. So plug in those values and then the easy cancellations. So you will see that the probability of getting a red ball in the second draw is R divided by R plus B. In a similar fashion, one can show that probability of B2 is B divided by R plus B. Note it down if you want. So, sorry, and note that P of R2 is same thing as P of R1. And similarly, PB1 equal to PB2. However, note that probability of R1 intersection R2, you can easily check this, is not the product of these two probabilities. So R1, R2 are not independent events.
Sorry, sir, I got disconnected for some moment. Can you please repeat the last argument?
Which one? Here, the
next slide.
Did you get up to this?
Yes. The next slide, first argument, sir.
Yes. See, we have noticed, say for example, what we have, the expression we have got for P of R2 is R divided by R plus P, which is same thing as P of R1, right? So similarly, concerning P of B2, it is equal to P of B1. So though these two probabilities, the probability of getting a red ball in the first draw is same thing as the probability of getting a red ball in the second draw, these events R1 and R2 are not independent events because you can easily check the probability of this intersection is not equal to.
I got it. I didn't see the whole thing. Okay, sorry, sir.
It doesn't matter. Okay. So from the above, one may say very often when you see some kind of a pattern maybe emerging, one tries to guess the answer. So we may guess that P of R1 is same thing as P of R1, namely the same quantity, R divided by R plus B. And similarly, P of Bn is same thing as P of B1, which is B divided by R plus B for all n. So this is a reasonable guess. You may all agree. So when you have that kind of a guess, you would like to prove it. And usually one of the methods, popular methods for proving such things is to use induction. So we are going to use induction to establish this. So when you apply induction, I think many of you would have seen earlier in some context or other, perhaps proof of binomial theorem and various things. One has to choose the appropriate induction hypothesis. So sometimes the choosing the induction hypothesis will have to be done judiciously. And this is one case. So the induction hypothesis is going to be the following. We will assume that this kind of an expression holds for n equal to 1 to up to k, and induction requires that using that information, you prove it for k plus 1. However, the induction hypothesis, we make it a kind of general one, not for this particular little r and little b and little c, for any number r, b, and c. That is, the hypothesis is, if we begin with capital R red balls and capital B black balls and add C balls of the same color as the drawn ball at each stage, probability of drawing a red ball at nth stage for n going from 1 to up to k is R divided by R plus B, and probability of drawing a black ball at nth stage is B divided by R plus B. So this is our induction hypothesis. In other words, we choose the induction hypothesis is that kind of a procedure, this thing holds for up to n equal to k, whatever may be this r, whatever may be the value of this little r, little b, little c. Since here these things stand for a special this thing, we choose general. Here the capital R, capital B, capital C stand for general finite numbers. Possible.
But since it is the induction hypothesis, it should be drawing a red ball at the kth stage, right? Instead of n.
No, wait. See, the induction hypothesis is very often that is why I have sort of written in italics. The hypothesis has to be chosen carefully. Okay. There are many instances in mathematics where the induction hypothesis is not just for that R, B, and C under consideration, but for any general R, B, and C. Okay. There is mathematically nothing wrong here.
No. I am saying that since you have pretended, we shall assume that for n equal to 1 to k, then at the last but one line, probably drawing a red ball at the kth stage instead of n, because n will going to prove for particular n.
Yeah. No. What I'm saying is n varies here. So in this thing, n varies over all these integers.
Yeah.
Up to k.
Yes.
In the proof, you will be using it as you say for k.
Yeah.
So the hypothesis is that this holds whenever n is less than or equal to k. And the proof will be when n is equal to k plus 1.
Yes.
Okay. This is a slightly tricky these things, because this kind of choosing the induction hypothesis in many contexts will have to be done carefully. All right. Okay, I'll go to the next slide, if you please. So we shall prove it now for n equal to k plus 1. Suppose if we begin with little r red balls, little b black balls, little c balls are added at every instant, then the probability of drawing a red ball at the k plus 1th stage, given that we have drawn a red ball at first stage. So that is what I have written out here. Probability of drawing a red ball at k plus 1th stage if a red ball is drawn at first stage. So that is same thing as, so we are given a red ball has been drawn at the first stage. So at the beginning of the second stage, we have little r plus little c red balls and just little b black balls, and c balls are going to be added. I mean, I have it, that's c. This. So it is same thing as drawing a red ball at kth stage, starting with this r plus c, b, and c, little c. And for this probability, for this equation, we are, in this context, we are applying the induction hypothesis. Because this particular event concerns, starting with a certain number of red balls, black balls, and the C balls to be added at appropriate stage, appropriately, probability of drawing a red ball at kth stage. And by induction hypothesis, it is R plus B divided by, little r plus C divided by R plus B plus C. Okay. Again, many of you would have seen it in your earlier course. This is a standard example in many first book on probability. Okay. Sorry. Yeah. So what we have got here is P of R k plus 1 given R is R plus C divided by R plus B plus C. And similar, using the induction, probability of drawing a red ball at k plus 1th stage, given a black ball has been drawn in the first stage, is R divided by R plus B plus, by that induction hypothesis to that situation. So using this information, since we have this and that other thing, we can compute probability of R k plus 1. And if you simplify these things, it turns out to be R divided by R plus B. So we have got probability of R1 equal to P of Rn equal to P of R1, that is equal to R divided by R plus B. And similarly, PBN is probability of B1, which is B divided by R plus B. So kindly note it down. Yeah, so that proves our thing concerning Polias and scheme.
Are there any implications of this result?
See, implications in the sense, we will not be seeing it in this course. Polia and scheme, there are several such schemes. See, these things, the kind of model which was coined by Polia when he was some kind of by having to make a mathematical model for certain contagious diseases. In the sense that, see, if a person is detected to be positive for a particular contagious disease, then the kind of probabilities, how they may have to be sort of suitably modified and things like that. And for more information on these things, you may look at, I think, Feller's book, Feller Volume 1, and schemes. So this is a fairly popular model in study of the contagious diseases. So this has actually obtained from an application. Okay. So at this stage, I'll just, it is being illustrated just as an interesting example of conditional probability. And also sometimes the C can be negative. That is, the person who is detected to have the disease is removed from the population, and so on. So many of these kind of things are discussed in Feller's book. Okay, now today's thing we will conclude with very elementary result, which is generally you will find it is being used in many places, and which is also easy to see. Suppose ANs are even such that A1 is contained in A2, etc., etc. That is, it is an increasing sequence of events. And let us say A is the union. So the increasing sequence of events, and the union is also in script A, that is A. Then the result says is P of A is limit of probability of AN. So that is the first part of the result. The second part is something similar for decreasing sequence of events. Bn are all events such that B1 contains B2, which in turn is contains B3 and so on. That's a decreasing sequence of events. Then we know that the intersection of the BIs, which we denote by B, is also an element of this script A. So the probability of B is limit of probability of B. So when the events are, you have an increasing sequence of events or a decreasing sequence of events, the finding the probability of their union or intersection respectively is this. Proof is very simple. Yeah, first of all, these are all numbers between 0 and 1. And since AN is contained in AN plus 1, probability of AN is less than or equal to probability of AN plus 1. So it is an increasing sequence of numbers which is bounded. So bounded monotone sequence. So the limit exists. Therefore, this limit makes sense. This makes sense. There is no problem about this being undefined. And similarly here. Okay. So therefore, this limit exists. Now, what we do is, since this is an increasing sequence of events, we take C1, we define new sequence C1, C2, etc., which are going to be disjoint. C1 is A1, C2 is A2 difference A1. That is, C2 is going to be all the points which are in A2 but not in A1, that difference. And we go on. Cn is AN difference, set difference, or set minus AN minus 1. So you can easily verify that each of these Cns are in script A. And also you can verify that these Cis are pairwise disjoint. That is, Ci intersection Cj is empty if I is not equal to j. Another thing also you can verify is that for each n, an can be written as union of Cj, j going from 1 to n. And this is a disjoint union. So this is also part of verify that. And also similarly here. So union an is equal to union cn. So once we do that, the proof is extremely simple now. Since A is equal to union Cn, and since this is a disjoint union, we have P of A is, which is probability of union Aj, which is same thing as probability of union Cj, and the Cj's are disjoint. So it is J going from 1 to infinity P Cj. And since this is a convergent sequence, this is basically limit n going to infinity of summation j going from 1 to n of PCJ. That is finitely many terms, up to sum up to finite terms, and then take the limit. And again, by similar argument, what is given here is probability union over j going from 1 to n of Cj's. So which this set we have found, we have observed it is an. So we have this. Basically, the idea is that any increasing sequence of events can be written as union of disjoint sets, such that at each stage, the an is equal to union of all the Cj's which are with j less than or equal to n. Now, for the second part of the proposition, it is by complementation and using the first part. So put dn equal to bn complement. Then bn's are decreasing, the di's are increasing. And you can easily see that b, the complement of b is union of these dn's. Consequently, probability of B is probability of 1 minus BC. And this B complement we have written as union of this increasing sequence of events Dn. So P of BC is limit of probability of Dn. So this can be written as limit 1 minus PDN. This equality is where we apply part 1 in this, that is this quantity is equal to this quantity. So 1 minus PDN is 1 minus P of Bn complement, which is probability. So that sort of concludes our thing for today. So unless you want me to go over some slide, earlier slide, I will stop sharing. Okay. Yeah. The last proof, this thing, what is involved is this AIs are increasing sequence of that each small circle, I mean, each circle, the whole circle denotes corresponding AN. And the CNs are basically that annular regions, which I have marked here. So this kind of a diagram, a rough diagram, you can easily see what is involved in the proof. And the union of this thing A, which can be written as the union of all these small annular regions, disjoint union. That precisely is the idea of the proof. And when they are disjoint events, then the axiom of probability can be used for if they are disjoint, then probability of union AI is summation of probability AI. So that is all for today. And again, I'm stressed that my intention was not to discourage questions. Just you can ask any question.
Sir,
Yes.
will you be uploading the slides on Moodle?
Yeah, even the last class slide has been uploaded on Moodle. I had sent you the link also.
Okay, I'll check.
See, the thing is, this time, since see, the last 2 semesters, since it was only one batch, all the students from one particular batch, there was the group ID. So I could send easily from my email account. But now there are people from various classes who are seem to be having some interest. And therefore, it is. I asked. there seems to be no way that this could be made into some kind of a group. So the option for me is only to send you the class meeting announcements as well as the link to this thing in YouTube over the Moodle. This thing. So if you see the messages in Moodle or from my Moodle, you will be getting the messages in your email account.
Sir, we received the video links, but we can't see the slides on Moodle.
But you have to go to YouTube. That's in YouTube.
Sir, the PDF slides.
The PDF slides I will not be able to give every day because it might come to very, very small increments. And so today I will be sending one because it has completed one unit. Okay. The PDF notes, PDF copies of files of the notes will be sent maybe once in 2 days or once a week and things like that.
Okay, sir, that is fine.
Yeah, like I was doing last 2 semesters. That's what I was doing.
So basically, you will combine notes of 2 to 3 classes into a single note and then upload in Moodle.
Sort of, roughly.
Okay. So instead of doing per lecture, you are doing part 2 to 3 lectures, combining notes.
Right. I thought that's what I was doing last 2 semesters. See this particular online.
I think that's what was done in analysis 3 also. I mean,
That's what I'm saying. Last 2
Exactly, yeah.
Analysis 3 last year, first semester I taught. I did that. And then later on, last year, second semester, I taught analysis for DS analysis. That is where I did that. So those of you who have been part of these classes might already be familiar with that thing. But those who are from other sections, they may not be. So it is also for their information. I hope one can make a group out of all this who are interested in this thing. It is not able to, I don't know how to do that. And by the way, the evaluation, there will not be any homework or assignments. There will be a midterm exam which will have 40% weightage and a final exam 60% weightage. Okay, problem set will be sent once in a while. That is maybe when a particular topic is sort of complete and so on. Okay.
Typically, sir, there won't be any weightage on the assignments.
There will not be any assignment. This will just be called problem set. If you want to do it, you do it for your benefit. If you don't want, you don't need not. There is no this thing of submission.
So basically, problem sets, they are not meant for submission, right?
No, because there are no TAs for this course.
Okay. So there is only midterm and end term. Midterm 40% and end term 60%.
Yes, yes.
Okay. And sir, when will you send the first problem set? Roughly.
Probably by sometime next week or end of next week. So that you cannot expect it to be regular. It could be at most once in 3 weeks and things like that. Okay, that some particular kind of portion which are sort of can form one group will have to be put together. Okay. So in that case, now we will end the session and we will meet again Monday. Okay, have a nice weekend. Stay safe.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you, sir.